So, we talked about the physical layer parameters for an EDFA, which included the gain flatness, saturation power and so on. Now, the most critical parameter now we need to consider is what is the extent of noise added by the EDFA, right. So, we are going to spend some time in understanding the noise added by the EDFA and how it is going to affect our performance of the link. So, your output of your EDFA is G, which is the gain of the amplifier. Now, you are talking about, we are trying to write the field at the output of EDFA. So, let us say E in is your field at the input and G is the gain defined with respect to the power. So, which means with respect to field the gain becomes root G times my input. This is considering only the gain, but we know that in addition to that there is a noise that is added in the EDFA and that is what is represented by N of t. So, E out of t represents the output electric field. It is square root times G, where G is the power gain times the input plus the noise that is added by the amplifier, which is typically not warranted for. And where is this noise coming from? It is coming from the amplified spontaneous emission. Just to remind you, what is amplified spontaneous emission? There could be sections of EDFA which is not pumped, which is where there is no signal, or even in the presence of signal there could be some amount of spontaneous emission, a small fraction of spontaneous emission occurring in the system, and these spontaneously emitted photons will pose itself as the signal to the remaining length of the fiber, and so it becomes amplified spontaneous emission. And it is incoherent because it is not coherent with the signal, it is not getting emitted in accordance with the signal. And the other difference is also that you could have amplified spontaneous emission over the entire fluorescent band, emission band. So, you remember the last module we saw the optical spectrum. So, it is going to look like this. You have the peak signal power and then across the spectrum you have noise, and this is your ASE noise, and your P peak is your peak signal power. So, you can always think of eliminating the amplified spontaneous emission noise outside the signal band by using an optical filter. You can put an optical filter like this, which picks up only the signal power and then cuts out all the amplified spontaneous emission noise, out of band noise. Out of band noise can always be avoided, but you will still have, you cannot obviously filter out the signal. So, you will still always have a noise in the band of the signal, and that is what is called as the in-band noise. So, the worry is mostly about the in-band noise. So, it is a given that all EDFAs comes with filters which are not only for gain flattening. Now, it will also have a filter corresponding to the signal band, so that you are eliminating all the noise added out of band, right. So, even now what we are going to see is what is the influence of this in-band noise. So, first thing to understand is what is the power spectral density of this amplified spontaneous emission noise. So, how do you quantify the ASE noise? The quantification is through the power spectral density, and it is also considered to be a white noise. So, you can talk in terms of the PSD, and the PSD is represented as rho ASE. Rho represents the power spectral density of the amplified spontaneous emission noise. Not deriving this, but it is not too complicated to derive that. The power spectral density is twice NSP H nu G minus 1, where G is the power gain, and NSP is a spontaneous emission factor, and that is decided by N2 divided by N1 minus N2. Now, the intuition behind defining this is simply that larger is your inversion, more is the probability that the ions are getting de-excited through spontaneous emission. So, that is why you are defining the spontaneous emission factor as N2 divided by N1 minus N2. Now this is the power spectral density. So now you can find out the total ASE power, which is also called as PASE. If you multiply it with the bandwidth, you will get, so this is in watts per hertz. So if you multiply it with the total bandwidth, you will get the total ASE power. Remember, this is the optical ASE power. So if I have a signal, so let us say your signal has peak here, and let us say your bandwidth is this much, your allowed bandwidth in your system. So this is frequency, this is your carrier frequency omega c, or let me call this as FC, the carrier frequency, and let us say your modulation is at 10 gigabaud. So you allow, let us say, plus 10 FC plus 10 gigahertz and FC minus 10 gigahertz to pass through your system. Then this total band, if you are putting a filter of bandwidth, total bandwidth, let us say 20 gigahertz, then I should use this B as 20 gigahertz. Okay. So depending, again it depends on the filter bandwidth. If my filter band, I am using a 1 nanometer filter at 1550 nanometer, if I am using for instance 0.08 nanometer is corresponding to 10 gigahertz. So you know 0.1 nanometer would correspond to 12.5 gigahertz. So if I am using a 1 nanometer filter, it would correspond to 125 gigahertz, right. So if I put a 1 nanometer optical filter at the output of my erbium doped fiber amplifier, I am allowing a equivalent bandwidth of 125 gigahertz, in which case my B corresponds to 125 gigahertz. And depending on how large is my bandwidth of the filter, I would keep adding my ASE power into my system. And to quantify this ASE, it is twice NSP. NSP is the spontaneous emission factor, N2 by N1, N2 minus N1, times H nu corresponds to the frequency, G minus 1 times B. Now once we have quantified the ASE noise, we can now talk about what happens at the receiver, right. So in my photodetector, we want to now, so we were talking about optical spectrum earlier. So the noise that we were talking about in that sense is an optical noise, but whenever we measure signal to noise ratio, we measure in the electrical sense. So now we are trying to find out how this optical noise is getting converted to electrical noise. So you start with the photodetector I, the photocurrent I, and that is equal to the responsivity times the input power, which is RD times now input power to the photodetector. So you are saying that I have an amplifier followed by a filter, which is my ASE filter, followed by my photodetector. Okay. Now this photodetector now receives both the signal power and the signal field and the noise field. Earlier I had represented it as N of t, now I am representing it as E of n, just to be consistent with the notation E. Okay. So E sig plus E n mod square. Now the question is, what should I denote as E sig and what is my E n? Because E n is a wide band, I mean there is a large frequency dependence. So if you look at the plot, optical power density versus power spectral density versus the x axis is actually optical frequency. Okay. It's optical frequency, just like I drew in the previous slide. Here the center frequency of the laser, let me call it as F. The center frequency of the signal is called as is denoted as F. The red square is, the big red square is actually telling you the band over which I have the amplified spontaneous emission, and this bandwidth is from F plus B naught by 2 to F minus B naught by 2. Now this B naught or BO is the optical bandwidth. Now what is this optical bandwidth? It is a bandwidth of the filter you see we put a ASE filter at the output of my EDFA. So, optical bandwidth of that ASE filter is what we are representing as BO. Okay. Now, the signal is centered at frequency f. Around the signal, for a bandwidth of BO, you have the amplified spontaneous emission. Okay. Calculation of the electrical noise due to the amplified spontaneous emission. What we are going to do is we are going to take an infinitesimally small width at a separation delta f from the signal. Delta f is not the width of that band that we are considering. Delta f is a separation of the band that we are considering with respect to the signal frequency. So, I am considering a band which is shown as a red band, which is at a frequency f plus delta f, where f is the carrier frequency and the width of the band is infinitesimally small, right. So, I am considering a noise field at this specific frequency. Now, I am going to represent that signal field and noise field. That is what we have done in the equations below. The signal field at a frequency f gets represented by square root of power times e power j 2 pi f t, because it is located at the center frequency f, whereas a noise field at the frequency f plus delta f is square root of rho ASE, where rho ASE is the power spectral density. Because the width is very small, the power is the same as the power spectral density, times e power j, the frequency is at f plus delta f. Okay. So, if I have a signal field at f and a noise field at f plus delta f, and if I try to find out what is the consequence of having this signal field and the noise field simultaneously falling on the receiver, that is my current I, that is easy to find out. I just substitute this E sig and En in this mod square equation. So, I get root of P sig e power j 2 pi f t plus root of rho ASE e power j 2 pi f plus delta f t. Okay. So, I need to do the expansion of this mod square. So, that is what I have written next, root P sig e power j 2 pi f t, and this rho ASE is actually, this is not a multiplication f plus delta f, but this this indicates that, this bracket indicates that this power spectral density, or this is the power of the ASE at the frequency f plus delta f, okay, at this frequency f plus delta f. Now, what do you get when you expand this? You will get a term corresponding to mod square of this, which will just be a P sig. You will get a term corresponding to mod square of this, which will correspond to just rho ASE at f plus delta f frequency, right. Rho, in fact, you will get rho star f plus delta f. You will get P sig, root rho star, right. So, you will get similarly root P sig star. So, essentially signal beating with itself, noise beating with itself, but what is more interesting is the third term. The third term will have twice root P sig, root PASE, and it will be at a frequency which corresponds to e power j pi 2 pi f t times e power conjugate of e power j 2 pi f plus delta f. So, the beat frequency will be at delta f t, right. This kind of calculations we have done in coherent receiver. So, I am not going to repeat it. I can just tell you that the current at the delta f frequency is R d times 2 times, because this will be there will be 2 terms appearing like that. So, you will have 2 times square root of P sig rho ASE at corresponding to the frequency delta f, the beat frequency delta f, and you will have a term like e power j 2 pi delta f t and e power minus j 2 pi delta f t, which you can combine and write it as cos 2 pi delta f t. Okay. So, this is the term which now represents something that is unwanted. Which is the actual signal term? You want, the detector is actually looking for only the signal term, but in addition the noise is anyway, we know that whatever is unwanted is noise. So, what is wanted is only the signal. So, what is wanted is only the mod square of the first term, but you have two additional terms at the output of the detector just because your EDFA added some noise. Okay. And these two additional terms are referred to as, this is referred to as Signal-ASE beat noise. And the other term which I did not write, root ASE conjugate of that, this is called as AC beat noise. Assuming that the AC power is small, you know that when you have a signal into the system, I already showed you a spectrum, the AC actually comes down in the presence of the signal. So, in the presence of the signal, if we assume that the relative power of the AC is small, I can ignore the AC beat noise, but I cannot ignore the P-Sig-ASE, Signal-ASE beat noise, because the signal power is large. So, the signal beating with ASE will give me a large power, and that is simply noise power. That is something that I do not want. So, essentially the current at this delta F frequency, the beat frequency between the signal and this specific ASE that I considered, that is the noise, and I want to avoid that, or rather I want to quantify that noise. So, what we want to quantify is this beat. So, this is the spectrum again that I am showing. So, what I am trying to show you is that this P-Sig and this PASE is beating together, giving rise to a signal at frequency delta F. So, in the electrical spectrum, so I am showing the corresponding electrical power spectral density, you get a contribution at delta F frequency because of the signal and the ASE that is beating according to our calculation. But you see the ASE is not limited to frequency F plus delta F. Your ASE is extending from F to F naught plus F plus B naught by 2, which means that if I keep changing my delta F corresponding to the different ASE components, I will keep getting these contributions all the way up to the frequency B naught by 2. So, if I am talking about a 10 gigahertz system, the electrical power spectral density, so this red square now represents the noise. This is now noise because this is the beat frequency that I generated, which I did not want to generate. It came only because of the beat between the signal and the ASE, right. So, the electrical power spectral density I am showing you is that of the noise because of signal ASE beat noise, and it will extend all the way up to B naught by 2, because I can now say that, you know, I just in my earlier calculation I took a frequency F plus delta F, but I could potentially have ASE all the way up to frequency F plus B naught by 2, which means that in the electrical spectrum I can have noise up to B naught by 2. Okay. Now, what about this on the left side? I could have also considered a band like this, a red small band like this on the left side of my signal also. That would also lead to the same beat frequency. So, which means that effectively I should double my power spectral density. I have a contribution. What I am trying to say is I have a contribution at delta F frequency corresponding to two beat components, two Signal-ASE beat components. One signal beating with the ASE at a frequency F plus delta F, signal beating with the ASE at F minus delta F also will give a component at delta F frequency. Okay. So, whatever answer I will get, I will have to actually multiply it by 2 because there are two contributions. I will have to multiply it by 2 to get the actual power spectral density. We will keep that in mind. But let us try to calculate what is a power spectral density. How do you now calculate the power spectral density? It is a power per unit bandwidth. We have kind of found a current per unit bandwidth. I delta F is actually current per unit bandwidth. So, which means if I want to calculate the power it is proportional to the square of the current. So, I will just square the above expression. So, if I square the above expression, what do I get? I get 4 times Rd square P sig rho ASE, and average of cos square would be half, because I am just calculating the average noise that is falling on the receiver. So, I get 2 times Rd square P sig rho ASE. Okay. Now, what would be power spectral density? Power spectral density would still be the same number, because we calculated the rho ASE as something similar to unit bandwidth. So, this is my power spectral density. But remember, I had to multiply this by 2, because I have noise contribution from the ASE at f plus delta f and f minus delta f. So, I have to multiply this by 2. But at the same time, I should also remember that my signal could be of a specific polarization and my ASE could be of random polarization, which means when I wrote this expression I equal to Rd times E sig plus En mod square, I could add these fields only under the assumption that both the signal and the noise are of the same polarization. But I know for a fact that noise will have random polarization, which means that I have kind of overestimated this beat by a factor of half. Why factor of half? Because any random polarization can be now equally resolved as the combination of x and y, equal combinations of x and y. So, I double counted there. So, which means that to consider that I have to multiply it with a half. So, I multiplied with a 2 to consider the beat from either side of the signal, by multiplied with half to consider the effect of polarization of the noise with respect to random polarization of the noise. So, effectively my power spectral density of noise remains as 2 Rd square P sig rho ASE. Now, I will ask this question, is this electrical noise or optical noise? And the answer is that it ought to be a electrical noise, because I started with detector current and then I did a square of the detector current. I have already multiplied the responsivity with the optical power. So, what we are calculating is the power spectral density of Signal-ASE beat noise in the electrical domain, not optical domain. In the optical domain, the noise is simply here, 2 slides before. PASE is, we wrote this expression, PASE is equal to 2 NSP h nu g minus 1 optical bandwidth. So, this optical bandwidth, this will be the ASE optical power, but the consequence of having this ASE in the electrical domain is to give rise to an additional noise whose power spectral density is given by 2 Rd square P sig PASE. Okay. So, this is how the signal mixing with amplified spontaneous emission in the detector gives rise to noise. I will remind you, we ignored the ASE beat noise because of the fact that we presumed that the amplified spontaneous emission by itself is a low number. So, it beating with itself is going to be a smaller contribution. But if you were to do an accurate calculation, you will have to do the same process for the ASE beat noise.